Greetings and welcome to the Sleepy Cosmos channel. It's wonderful that you found your way here. Perhaps your day was long, or maybe you're the sort of person who prefers to drift off to sleep, contemplating profound ideas and cosmic enigmas, rather than counting livestock. Either way, tonight's exploration is crafted for you. You have nothing else to do but relax. Allow your thoughts to wander, your breathing to deepen, and your body to feel weightless, as if the very pull of gravity has lessened. Because this evening our journey is more than mere stargazing. We are venturing through our celestial home, the Milky Way, a colossal spiral of stellar bodies, interstellar dust, and unseen matter. It has been slowly rotating through the cosmos for over 13 billion years. Yet, within its magnificent expanse lie hidden truths, wandering stars, imperceptible forces, and ancient remnants that challenge our current understanding. We will navigate gently from its outlying spiral arms to its deeply concealed heart, from cataclysmic impacts to stars that predated the galaxy itself. You'll hear of black holes, stellar nurseries, and the peculiar ongoing saga of a galaxy still in development. Some of the revelations tonight may astonish you, or at the very least, pique your curiosity as you ease into slumber. And just before we commence, should these tranquil, thought-provoking explorations help you unwind or offer a peaceful conclusion to your day, please consider giving us a like and subscribing to the channel. This assists other seekers in discovering us as well, one peaceful soul at a time. Now let us begin. The Milky Way has already encountered and merged with other galaxies, and it will do so again. While our galaxy may seem like a steadfast abode, its very structure is composed of the remnants of others. Over eons, the Milky Way has assimilated lesser galaxies, drawing them inward, dismantling them, and scattering their stellar components into vast tidal streams that encircle its disk. One such galaxy, the Sagittarius dwarf, is presently being pulled apart. And far off in the night sky, Andromeda is steadily approaching. In approximately 4.5 billion years, the two immense spirals will converge in a grand cosmic embrace. While stars themselves will very rarely collide, the galaxy's overall forms will be irrevocably altered, coalescing into a new, expansive, and tranquil entity. Even galaxies are not immutable. They transform, merge, and are reborn. Some stars within the Milky Way are older than the Milky Way itself. Not every star residing in our galaxy originated here. Certain halo stars, ancient and sparse in heavy elements, traversing elongated, tilted orbits, appear to have formed even before the Milky Way had fully coalesced into its current form. Astronomers surmise that these stars may have emerged from smaller, primordial galaxies that merged with our own eons ago. Their elemental composition reveals a profound scarcity of heavy elements, indicating their birth shortly after the Big Bang. They move with a slow grace, high above the galactic plane, like venerable spirits from an era preceding organized structures. In their faint light, we perceive a universe that was younger, wilder, and still in the process of becoming. Our solar system traverses the Milky Way's center at a velocity exceeding 828,000 kilometers per hour. That equates to over 230 kilometers every second. Despite this immense speed, it still takes approximately 225 million years to complete a single circuit around the galaxy. This orbital path is known as a galactic year. In Earth time, our solar system has completed roughly 20 circuits around the Milky Way since its formation. When the first dinosaurs roamed the Earth, our solar system was situated in a vastly different region of the galaxy. The stars we observe today were not always in our vicinity, nor will they remain so. All existence is in perpetual motion, quietly, slowly, eternally. Even as we slumber, the Earth turns, the Moon orbits, and our entire solar system sweeps forward through a galaxy in constant flux. The galaxy continues to expand. Although the Milky Way is ancient, its evolution is not complete. It continues to gather material, drawing in gas from the intergalactic medium, stars from captured dwarf galaxies, and streams of dark matter that replenish its halo. Its growth is not akin to biological life, but rather a gravitational structure deepening over time. Some of this accretion occurs subtly through the assimilation of gas clouds. At other times, it involves disruption, as satellite galaxies are torn apart and their stars dispersed across the celestial sphere. The galaxy you inhabit today is not identical to the one observed by the dinosaurs, and the galaxy your distant descendants may know could be even more substantial, stitched together from the remnants of countless smaller worlds. We do not precisely know the number of arms the Milky Way possesses. It seems a fundamental piece of knowledge about our galactic home. How many arms spiral outwards from the galaxy's core? Yet, from our vantage point deep within the disk, discerning the entire structure is challenging. Obscuring dust clouds hide distant regions, and stars blur into a single luminous haze. For decades, astronomers believed there were four primary spiral arms. More recent observations suggest a potentially smaller number, or that the arms exhibit a more intricate twisting and branching than previously thought. Some arms fragment, while others unexpectedly loop back. The Milky Way may not be a neat pinwheel at all, but rather a complex, layered swirl of stars shaped by forces we are still endeavoring to fully comprehend. Rogue stars are expelled from the core. While most stars traverse the galaxy at a steady pace, a select few are ejected at astonishing velocities, fast enough to escape the Milky Way's gravitational pull entirely. These are known as hypervelocity stars. Some originate from binary star systems that have been disrupted by the supermassive black hole at the galaxy's center. When one star is drawn into the black hole and vanishes, its companion is violently propelled outwards, hurled into the void at speeds exceeding 1 million kilometers per hour. These rogue stars journey alone, far from the galactic plane, resembling luminous comets with no destination. They serve as a reminder that even within a galaxy governed by gravity, moments of intense release occur, quiet expulsions that send stars hurtling into the intergalactic night. The Milky Way and Andromeda are on a collision course. High above the horizon, the Andromeda galaxy appears as a faint, hazy patch to the naked eye. A spiral galaxy much like our own, situated over 2 million light-years away. Nevertheless, it is steadily moving toward us. In approximately 4.5 billion years, the Milky Way and Andromeda will collide. This encounter will not be violent in the manner one might typically imagine. Stars are too widely spaced to directly impact one another. However, their mutual gravitational influence will distort both galaxies into elongated arcs. Tidal tails will extend outwards, and black holes may spiral together. Ultimately, after billions of years, the two galaxies will merge into a single, larger cosmic entity. It will be a slow, elegant transformation, the future of our home written across the stars. Some stars orbit in reverse. The majority of stars in the Milky Way revolve around the galactic center in the same general direction. However, not all adhere to this pattern. Certain stars, particularly those in the outer halo, exhibit retrograde motion, orbiting in the opposite direction to the galaxy's primary rotation. These stars likely originated elsewhere, born in dwarf galaxies that were subsequently absorbed by the Milky Way. Their reversed orbital path serves as a subtle indicator of their foreign genesis. It is as if the galaxy retains ancient memories within its motion, narratives of past mergers and cosmic encounters, preserved not in visible light, but in the slow, deliberate rotation of stars against the prevailing current. The Milky Way has likely consumed dozens of dwarf galaxies. It has not grown in isolation. It has assimilated. Small galaxies, faint companions, have drifted too close, been ensnared by its gravity, and gradually dismantled. Their stars are now integral components of our halo, disk, or stellar streams. Astronomers have identified numerous such mergers through the analysis of stellar motion and chemical composition. One particularly significant event, the Gaia-Enceladus merger, contributed a substantial number of stars and may have reshaped the galaxy's early structure. The Milky Way is not a pristine spiral. It is a composite forged from quiet collisions and assembled from the remnants of numerous smaller worlds. The chemical makeup of stars reveals their origin. Every star bears a unique elemental fingerprint, a pattern of elements imprinted at its birth. By examining these signatures, astronomers can trace a star's history. Some stars are rich in heavy elements like iron and calcium, suggesting they formed in dense, metal-rich environments. Others are composed almost entirely of hydrogen and helium, born when the universe was still in its infancy. These disparities allow scientists to categorize stars into distinct populations, uncover ancient mergers, and reconstruct the hidden evolutionary path of the Milky Way. In this manner, chemistry becomes a form of time travel, enabling us to read a star's past like an ancient poem written in light. The sky is replete with stellar streams from shattered galaxies. Across the celestial sphere, delicate ribbons of stars stretch in arcs and curves, barely perceptible but unmistakable when precisely mapped. These are stellar streams, the remnants of smaller galaxies that ventured too near the Milky Way and were torn apart. As they orbit, their constituent stars are spread across space by tidal forces, forming long, ethereal trails that trace their former trajectories. Some encircle the galaxy like ghostly coronas, while others plunge towards its core. These streams bear witness to past collisions, quiet mergers that have shaped the Milky Way over billions of years. The galaxy, much like a tree, carries the rings of its past within every thread of light. The Milky Way is warped. Our galaxy does not lie perfectly flat like an idealized spiral. Its disk bends upwards on one side and downwards on the other, creating a graceful wave across the starry expanse. This subtle warping remained imperceptible until radio telescopes mapped the hydrogen gas extending far beyond the visible starlight. Astronomers theorize that this distortion may be caused by the gravitational tug of satellite galaxies on the Milky Way's periphery, or by clumps of dark matter subtly bending the structure from below. Like ripples on a vast spinning tablecloth, the warp demonstrates that even galaxies are in a state of perpetual, dynamic change, bending, flexing, and altering their forms in response to unseen influences. From a distance, the Milky Way might appear to be engaged in a slow, deliberate dance through space. We can observe only approximately 0.00003% of the Milky Way with our unaided eyes. Under a clear, dark sky, far from the pervasive glow of urban areas and artificial lighting, you might perceive a few thousand stars. To the human eye, this appears as an oceanic expanse of light, yet it represents merely a minuscule droplet. The Milky Way contains over 100 billion stars. The vast majority remain concealed. Some are hidden behind dense veils of cosmic dust, while others are too faint or distant for our vision to resolve. The pale, ethereal streak of the Milky Way that bisects the night sky on moonless evenings is but the faintest whisper of its totality. We exist surrounded by a colossal river of starlight, and yet nearly all of it remains imperceptible to us, too immense to be comprehended from within. Stars orbit the galaxy at varying velocities. Unlike planets in a solar system, which follow predictable trajectories around their star, stars within the Milky Way exhibit greater freedom of movement. Some race at high speeds in the inner regions, while others drift leisurely along the outer edges. This differential velocity is the reason spiral arms form. They are not solid structures, but rather emergent patterns, akin to slow-moving traffic jams of stars and gas navigating through space. As these density waves propagate, they compress gas clouds, triggering the formation of new stars, illuminating the arms with incandescent curls of blue and white. Our own sun is part of this grand swirl, periodically moving in and out of these patterns over time. The galaxy is not a rigid mechanism, it is a fluid current, and we are carried within it. The galaxy remains cohesive due to an element we cannot perceive. By all logical estimations, the Milky Way should not persist. Based on our measurements of stars, dust, and gas, the outer edges of the galaxy are rotating too rapidly. They should be flung outwards into space, scattering like leaves in a tempest. Yet, they remain bound. The explanation lies in dark matter. This enigmatic substance emits no light, reflects none, and is invisible. However, it exerts a gravitational influence, and its abundance is so significant that it outweighs all visible matter in the galaxy by many orders of magnitude. We do not yet understand the nature of dark matter, but we know that without it, the Milky Way would disintegrate. It serves as the invisible scaffolding that holds everything in place. At its heart lies a supermassive black hole. At the very center of the Milky Way resides an immense black hole, a point of singularity known as Sagittarius A. It possesses a mass exceeding 4 million times that of the Sun, yet it occupies a region smaller than the orbit of Mercury. While we cannot observe it directly, we have witnessed nearby stars performing tight, rapid orbits around it, tracing invisible paths through the void. Occasionally, gas and dust are drawn inwards, flaring with X-rays as they spiral towards the event horizon. For the present, Sagittarius A rests quiescently. However, in epochs past, it may have blazed like a quasar, illuminating the galaxy from within. It is the silent conductor of the Milky Way's core, orchestrating a slow, inexorable cosmic ballet of stars. The Milky Way possesses a peanut-shaped bulge. When astronomers mapped the galaxy's central region, they discovered an unexpected feature. The central bulge is not a smooth, spherical concentration of stars, but rather a three-dimensional peanut-like structure. When viewed from the side, it swells in its middle and tapers at its extremities, resembling an hourglass of stars in motion. This unusual geometry likely originated from the galaxy's central bar, a dense band of stars that rotates slowly, buckling and expanding upwards over time. These internal structures are shaped by gravitational forces, billions of years of celestial motion, and the accumulated rhythm of stellar orbits. We reside within a spiral galaxy, yet its heart is a place of profound complexity, not flat and orderly, but intricate and vibrant. Stellar nurseries sculpt the spiral arms. The Milky Way's spiral arms are not merely composed of stars, they are interwoven with the very birthplaces of stars. Vast clouds of hydrogen, dust, and molecules drift throughout the galaxy. As these clouds traverse the spiral arms, they are compressed, igniting with the birth of new suns. These regions are designated as stellar nurseries, characterized by chaos, luminosity, and incessant motion. Ultraviolet radiation from newly formed stars illuminates these clouds, painting the arms with radiant hues of blue and silver. These bursts of creation trace the spiral form, imbuing the galaxy's curves with a soft, internal fire. Every star, including our Sun, originated from one of these nebulous cradles countless ages ago. The Milky Way is encircled by a vast halo. Beyond the broad, flattened spiral disk lies a far more diffuse structure, a spherical halo that encompasses the entire galaxy. It contains ancient stars, globular clusters, and immense quantities of dark matter. Despite its near invisibility, this halo may contain the majority of the Milky Way's mass. Its stars are thinly dispersed across immense distances, executing long, slow orbits that seldom intersect the disk. The halo also preserves the remnants of ancient galactic mergers, presenting as streams and shells of stars torn from smaller galaxies and left behind like cosmic fossils. It represents the galaxy's external memory, quiet and dim, yet still in motion, continuing to influence the Milky Way's future form. It contains over 150 globular clusters. Globular clusters are among the galaxy's most ancient celestial objects. These are dense spheres comprising hundreds of thousands of stars bound together in close proximity. They orbit the galactic center within the halo, much like moths drawn to a distant flame. These clusters exhibit remarkable stability, some exceeding 12 billion years in age, and many contain stars that predate the Milky Way itself. Their stellar populations are metal-poor, indicating their formation occurred before the universe had synthesized many of the heavier elements. They function as time capsules, holding vital clues about the galaxy's formation, its assimilated constituents, and the conditions prevalent in the early cosmos. These placid golden spheres drift patiently above and below the galactic plane, their faint glow illuminating the darkness. The galaxy is still expanding. Despite its immense age, the Milky Way's evolution is ongoing. Even now, it continues to accrue material. Gas from the intergalactic medium, stars from captured dwarf galaxies, and streams of dark matter that contribute to its halo. Its growth is not analogous to that of a living organism, but rather that of a gravitational structure deepening over time. Some of this expansion transpires silently through the assimilation of gaseous clouds. At other junctures, it is accompanied by disruption, as satellite galaxies are torn asunder and their stellar components dispersed across the sky. Rogue stars are flung from the core. While most stars traverse the galaxy at a steady pace, a select few are ejected at astonishing velocities, fast enough to escape the Milky Way's gravitational pull entirely. These are known as hypervelocity stars. Some originate from binary star systems that have been disrupted by the supermassive black hole at the galaxy's center. These rogue stars journey alone, far from the galactic plane, resembling luminous comets hurtling into intergalactic night. Star formation is diminishing. In past eras, the Milky Way was a more dynamic entity, teeming with nascent stars born from dense, collapsing gas clouds. However, in recent epochs, the rate of star birth has slowed. While gas remains available, much of it is now thinly dispersed, heated, or exists in forms that resist gravitational collapse. The galaxy is not ceasing its star production entirely, but its activity is becoming more measured. Astronomers estimate that star formation peaked billions of years ago and has been in gradual decline ever since. This does not portend an imminent end, but rather signifies that we are living in a more tranquil chapter of the galaxy's history. It is a mature spiral, glowing gently in its middle age, still forging stars, but no longer with the urgency of its youth. Some stars formed before the Milky Way possessed a disk. The disk, the broad, flat spiral structure that we commonly envision as the Milky Way, gradually took shape over immense periods. However, some stars within our galaxy are older than the disk itself. These ancient stars are predominantly found in the halo, or the thick disk, and they originated when the galaxy was still in the process of assembly, a loosely organized collection of stars, gas, and dark matter slowly collapsing inwards. By examining their elemental composition and orbital patterns, astronomers can glimpse into the era that preceded structured organization before the emergence of spiral forms. These stars are the elders of the galaxy, silent witnesses to its genesis and the prolonged, gradual formation of what we now call home. A galactic year is approximately 225 to 250 million Earth years. As the Sun orbits the center of the Milky Way, it completes one full revolution, roughly every few hundred million years. This period is referred to as a galactic year, a vast cycle of motion that dwarfs all our terrestrial calendars. In the span of time it takes for the Sun to complete one circuit of the galaxy, continents drift, species emerge and vanish, and entire eras unfold. It is believed that we are currently approximately halfway through one such orbital period. The last time our solar system occupied this segment of its path, the supercontinent Pangaea was just beginning to fracture, and dinosaurs had not yet appeared. A galactic year represents the slow, deliberate pulse of cosmic time. The Sun has completed fewer than 25 galactic orbits. In its entire 4.6 billion years of existence, the Sun has circled the Milky Way only around 20 times. This number is less than one might anticipate, given its astonishing velocity of nearly 830,000 kilometers per hour. However, the galaxy's immense scale and the Sun's lengthy orbital path mean that each revolution requires hundreds of millions of years. We often perceive stars as ancient and immutable, yet our solar system is comparatively young on a galactic timescale, a newcomer in a metropolis populated by older, more seasoned suns. We are participants in the galaxy's grand motion, but still in the early stages of its long and winding narrative. The Milky Way's rotation defies Newtonian predictions. According to classical Newtonian physics, stars situated farther from the galactic center should orbit at slower speeds, much like the outer planets move more leisurely around the Sun. However, within the Milky Way, stars in the outer regions orbit at nearly the same velocity as those closer to the center. This observation contradicts classical expectations. The prevailing explanation, according to astronomers, is the presence of dark matter, an invisible, unknown form of mass that envelops the galaxy in a vast halo. Without dark matter, the galaxy would simply not remain gravitationally bound. With its inclusion, the mathematical models align. The Milky Way rotates as if it were a solid disk, not because we fully comprehend its mechanics, but because an unseen entity is maintaining its structural integrity. The galaxy harbors enormous molecular clouds. Dispersed throughout the Milky Way are vast, dark clouds of frigid gas, serving as the fundamental building blocks for stars. These molecular clouds, composed primarily of hydrogen molecules and trace amounts of dust, can span hundreds of light years. Within their cold, dense interiors, gravity begins to aggregate material, forming clumps that subsequently collapse to give rise to new stars and planets. Some of these clouds are so immense and so cold that they entirely absorb visible light, appearing as dark patches against the backdrop of stars. They are the galaxy's wombs, secluded and silent regions where the future emerges in stillness, nestled within shrouds of shadow and gas. Supernovas agitate the galaxy like storms. When colossal celestial bodies conclude their lifespans, they detonate in cataclysmic supernovas. These occurrences are so potent that for a fleeting instant they can outshine entire galaxies. These bursts don't merely extinguish lives, they foster new beginnings. The shock waves emanating from supernovas reverberate through the interstellar medium, compressing adjacent nebulae and igniting fresh cycles of stellar generation. They imbue the surrounding cosmic expanse with weighty elements such as iron and gold, synthesized within the core of the expiring star. In this manner, supernovas function as storms within the galactic ecological system, agitating, nurturing, and reshaping everything in their vicinity. They represent the galaxy's periods of upheaval, both destructive and incandescent, and crucially, indispensable. Dust conceals immense domains of stellar genesis. Our Milky Way galaxy is replete with luminosity that remains imperceptible to us. Interstellar dust, comprised of minuscule particles of carbon, silicon, and ice, pervades the galaxy in the form of clouds and wisps. In visible light, this dust obscures vast swathes of space, obscuring stars and entire nebulae. However, concealed behind this veil, the creation of stars persists. Infrared telescopes possess the capability to penetrate this dust, revealing radiant stellar nurseries teeming with nascent suns. What appears as darkness often serves as a cradle. The dust, while it conceals, is an integral component of the process, absorbing energy, facilitating gas cooling, and safeguarding delicate phases of stellar birth. What seems like emptiness is frequently the genesis of something brilliant. There exist starless gas clouds adrift throughout the galaxy. Not every gaseous nebula matures into a star. Across the expanse of the Milky Way, astronomers have identified immense frigid clouds that appear destined for collapse, yet they remain devoid of light and inert. Certain clouds are excessively diffuse, others might be stabilized by magnetic fields or internal turbulence. These starless clouds float through the galaxy like silent potential. They are rich in molecular hydrogen, but untouched by nuclear fusion. They may eventually ignite, or they might drift until torn apart by external forces, their gas recycled into other regions. Within these clouds, the galaxy appears to hold its breath, perhaps awaiting the opportune impetus to ignite something new. The Milky Way reprocesses matter across successive generations. Stars are not eternal entities. They exist, burn, and perish, and in their demise they return their constituent materials to the galaxy. Supernovas disseminate heavy elements. Red giant stars shed their outer envelopes. Planetary nebulae disperse outward into space. This enriched material merges with the interstellar medium, where it cools, coalesces, and ultimately forms new stars, planets, and even life. Every atom within your being has traversed this cycle, born within a star, dispersed into the cosmos, and reassembled into new forms. The Milky Way is not a static backdrop, but a grand mechanism of regeneration. It breathes in rhythm with its stars, creating, dismantling, and beginning anew. Stars with a deficiency of heavy elements hold clues to the early universe. In the realm of astronomy, metals encompass not merely iron or gold, but any elements heavier than helium. The universe's earliest stars contained virtually none of these metals because they formed prior to earlier stellar generations, having the opportunity to forge and disperse them. Presently, astronomers seek out metal-poor stars within the halo of the Milky Way. These stars, faint and ancient, preserve the chemical conditions of a bygone era. By examining their elemental composition, we gain insight into the primordial past, the epoch immediately following the Big Bang, before galaxies had fully matured, and before the galaxy itself had taken definitive shape. They are essentially fossils constructed from light. Certain stars wander far from their points of origin. A star's birthplace does not invariably dictate its ultimate fate. Over extended periods, numerous stars drift away from their native nebulae, propelled by gravitational interactions, orbital resonances, or the gradual influence of spiral arms. Some stars are expelled at considerable velocities, flung across the galactic disk or into the halo. Others migrate incrementally, their orbits shifting inward or outward as they spiral through the galaxy. Even our own sun has not remained in its original location. By tracing the trajectories of stars, we observe a Milky Way that is anything but stationary. It is a galaxy alive with motion, exchange, and subtle shifts in position. A star's celestial dwelling may be transient. The habitable zone of the galaxy could span tens of thousands of light years. Just as Earth orbits within a Goldilocks zone around the Sun, maintaining a temperature neither too hot nor too cold for life, the Milky Way might possess its own galactic habitable zone. This region is theorized to lie between the perilous inner core, saturated with radiation and gravitational chaos, and the sparse, metal-poor outer extremities, where planet formation might prove more challenging. Somewhere in between exists a broad band where conditions are stable, stellar density is moderate, and elements such as carbon, oxygen, and iron are abundant. Earth resides within this zone, a tranquil orbit in a vast cosmic swirl where life may not be unique in finding a secure foothold. The spiral arms are not immutable structures. The Milky Way's spiral arms might appear as permanent formations, grand, sweeping lines etched into the galaxy's disk, but they are not comprised of static stars. Instead, they are patterns, density waves that slowly ripple through the disk, compressing gas and stimulating the birth of new stars as they pass. Stars drift into these arms, shine for a period, and then drift away again. The spiral structure propagates at a different velocity than the stars themselves, akin to a traffic jam moving along a highway. From a distance, it conveys an impression of form and order. From within, it is a pattern of shifting movement, held together by gravity and time, perpetually in motion and ceaselessly flowing. The Milky Way resonates with cosmic radiation. Beyond the visible spectrum, the galaxy emanates with more enigmatic forms of energy. Cosmic rays, high-energy particles originating from supernovas and distant galaxies, stream through space and pass through your body every second. X-rays and gamma rays shimmer from dying stars and black holes. Radio waves emanate from gas clouds, pulsars, and the faint emission from hydrogen. These imperceptible hums reveal phenomena that visible light cannot. They disclose the violence, magnetism, and ancient fires still flickering within the galaxy's fundamental structure. When you gaze upon the night sky, you are observing merely a narrow segment of the Milky Way's true energetic spectrum. Beneath the visible stars, the galaxy emits a soft hum across a multitude of frequencies and colors, a hidden symphony veiled in darkness. There is a colossal gamma-ray bubble situated above and below the galactic center. Extending tens of thousands of light-years above and below the galactic core are two vast ethereal lobes of high-energy light. These are the Fermi bubbles, discovered only recently. They glow in gamma rays, appearing like twin balloons emanating from the heart of the Milky Way. The precise cause of their formation remains uncertain. They could be the remnants of a long-ago outburst from the central black hole or evidence of intense star formation that once flared through the core. Regardless of their origin, these immense structures drift silently above the galaxy, invisible to human sight. They serve as a reminder that the Milky Way possesses a past that we cannot fully apprehend. They are echoes of violence enveloped in radiance, positioned far above the stars we recognize. We reside in a minor spur situated between major galactic arms. Our solar system is not located within one of the Milky Way's prominent spiral arms. Instead, we inhabit a modest structure known as the Orion Spur, a relatively tranquil stellar lane nestled between the larger Sagittarius and Perseus arms. This region is neither particularly dense nor exceptionally active, but that very tranquility might be the reason for our presence. In the calm interval between major galactic thoroughfares, colossal supernovas are infrequent. Radiation storms are less common. This serene corner may have provided life on Earth with the necessary time for its emergence and evolution. From the periphery, the galaxy appears dramatic and radiant. However, within this quiet spur, we found precisely enough tranquility for complexity to unfold. The Milky Way possesses a bar-shaped central structure. When astronomers direct their infrared telescopes toward the galactic core, they observe not a perfect circle, but a thick, elongated bar of stars extending across the center, akin to a glowing bridge. This bar rotates slowly, and its gravitational influence shapes the inner spiral arms. Bars of this nature are common in spiral galaxies. They form when stars in the disk begin to drift inward and accumulate along a central axis. Over time, the bar develops into a stable structure, agitating gas, stimulating new star formation, and channeling material toward the supermassive black hole at the galactic center. It is not merely a shape, but a dynamic engine, sculpting the galaxy's heart from within. It is part of a larger structure known as the local group. The Milky Way does not exist in isolation. It is part of a conglomerate of over 50 galaxies known as the Local Group, a small cluster drifting together through space. The two most massive members are the Milky Way and Andromeda, each accompanied by its own retinue of satellite galaxies. Scattered around them are smaller dwarf galaxies, faint elliptical galaxies, and star-filled galaxies composed almost entirely of dark matter. The local group spans more than 10 million light-years and is bound not merely by proximity, but by gravity. We are part of this galactic family, quiet and widely separated, yet still connected by the unseen threads of shared motion and mutual gravitational attraction. Galaxies within the local group are gravitationally bound. Despite their immense distances from each other, the galaxies of the local group are not drifting apart. In fact, many are slowly moving toward one another. Gravity orchestrates their movement in a slow-motion ballet, curving their trajectories over millions of years. Some of the smallest galaxies orbit the Milky Way like moons, circling and falling, eventually dissolving into streams. Others drift independently but remain tethered, caught within a web of shared cosmic motion. Over time, this group may condense further. Galaxies might merge, fade, or be absorbed. This is not a static arrangement, but a gentle congregation of cosmic islands, a family drawn closer by time, inertia, and the far-reaching influence of gravity. The galaxy's disk comprises both thick and thin components. From a distance, the Milky Way's disk appears flat, but upon closer inspection, it reveals distinct layers. The thin disk is our immediate cosmic neighborhood, a broad, dense plain populated by young stars, open clusters, and star-forming gas. However, situated above and below it is the thick disk, which is older, more diffuse, and less densely packed. Stars in the thick disk tend to be older and possess fewer heavy elements. Their orbits are more inclined and elliptical, suggesting they formed under different conditions or were perturbed by early galactic collisions. The galaxy's disk is not uniform. It possesses texture, layering, and is shaped by time, much like sediment settling on the floor of a cosmic ocean. The galaxy's magnetic field threads through its disk. Although imperceptible to the naked eye, the Milky Way is permeated by a vast magnetic field that extends across the disk, rises into the halo, and weaves through the interstellar medium. This field, while weak by terrestrial standards, exerts a significant influence over galactic distances, dictating the pathways of cosmic rays, the collapse of gas clouds, and the flow of matter through space. It aligns with the spiral arms, forms arcs above the galactic plane, and twists into intricate loops that defy simple explanation. Its study necessitates the use of radio telescopes and meticulous analysis. However, its presence is undeniable. The Milky Way does not merely radiate light, it pulsates with magnetism, a subtle force coursing through its fundamental structure. The interstellar medium is replete with invisible structures. The space between stars is more than mere emptiness. The interstellar medium, a tenuous blend of gas, dust, and plasma, permeates the Milky Way like a pervasive fog. To the unaided eye, it is largely invisible. However, when observed through radio and infrared telescopes, it reveals a remarkable complexity. It manifests as filaments, bubbles, shock waves, and cold, dense clouds where stars are born. Supernovas carve out vast cavities within it. Stellar winds sculpt it into shapes that ripple across light years. The expanse between stars is not a void, but a dynamic network of matter and magnetism. It is the quiet substrate from which galaxies evolve and life eventually emerges. Cosmic rays perpetually traverse through us, originating from the galaxy. Every second, high-energy particles, primarily protons and atomic nuclei, stream through your body, having been propelled long ago by exploding stars. These are cosmic rays, and they are ubiquitous. They travel at speeds approaching the speed of light, bending through magnetic fields, rebounding off gas clouds, and occasionally colliding with atoms in Earth's atmosphere, where they generate showers of secondary particles. For the most part, we remain unaware of their presence, yet they carry narratives from across the galaxy, evidence of ancient supernovas, traces of distant acceleration events, and messages from the violent energetic processes within stars. Even in your moments of rest, the galaxy is communicating through particles, in silence, and via rays devoid of visible light. The galaxy is not symmetrical, although many diagrams depict it as a neat, even spiral. The Milky Way is not perfectly balanced. One side of its disk appears thicker. Some spiral arms are brighter, longer, or more curved than others. The warp in the outer disk is noticeably asymmetrical. Even the stellar populations between the hemispheres exhibit slight disparities. These asymmetries may be attributed to gravitational encounters, past mergers, or the influence of dark matter. They serve as a reminder that galaxies, much like living organisms, bear imprints of their histories within their shapes, displaying scars from collisions, wrinkles accumulated over time, and idiosyncrasies of uneven growth that bestow upon them character and depth. The oldest known star may be situated in our halo. High above the galactic plane, drifting through the halo, astronomers have identified a star that might be nearly as ancient as the universe itself. It contains an almost negligible amount of heavy elements, a characteristic signature of stars born shortly after the Big Bang, before successive generations of supernovas had enriched the cosmos. It likely originated over 13 billion years ago, long before the Milky Way had fully coalesced. It now burns quietly with a faint red luminescence, possessing low mass but an immense historical significance. It is not merely a star, it is a time capsule, a living relic from the universe's earliest dawn. The central region of the galaxy rotates faster than its outer reaches. In the inner regions of the Milky Way, stars orbit the galactic center at considerably higher velocities than those situated farther out. Near the core, the gravitational pull is more intense, concentrated by the mass of stars, dust, and the supermassive black hole known as Sagittarius A. This increased gravity causes stars to traverse tighter, more rapid orbits, completing revolutions in mere millions of years. In the outer expanses of the galaxy, analogous to where our sun resides, stars orbit more slowly, requiring hundreds of millions of years for a full circuit. This differential rotation generates twisting patterns, elongates spiral arms, and prevents the disk from behaving as a solid entity. The galaxy moves like a colossal wheel, but one whose periphery lags behind its hub. Spiral arms are shaped by density waves. The spiral arms of the Milky Way are not fixed trails of stars. Rather, they are patterns formed by waves of increased density propagating through the galactic disk. As gas and dust traverse these waves, they are compressed, triggering star formation and illuminating the arms with brilliant young stars. These stars eventually drift out of the wave while new ones form behind them, creating a self-sustaining illusion of structure. Akin to ripples on a pond or congestion on a highway, the arms are dynamic and constantly in motion. From a distance, they appear static. From within, they are a dance of matter and rhythm, sculpted by gravity and time. Stars are born from cold, collapsing gas. Within the darkened arms of the Milky Way, star formation commences in silence. Massive clouds of molecular hydrogen, occasionally spanning hundreds of light years in diameter, drift through space, chilled to mere degrees above absolute zero. Within these clouds, gravity gradually asserts its influence. Small regions increase in density and begin to collapse under their own gravitational pull. As the gas falls inward, it heats, spins, and flattens, forming a protostar at the center. Over time, the internal pressure and temperature escalate until nuclear fusion ignites, marking the birth of a new star. From the coldest shadows emerge the brightest lights, gently spun into existence by the quiescent force of gravity. Star clusters can disperse into the galactic field. Many stars originate not in solitude but in groups. These are tightly bound clusters formed from the same collapsing gas cloud. Held together by mutual gravitational attraction, these clusters drift collectively for millions or even billions of years. However, over extended periods, they begin to scatter. Tidal forces exerted by the Milky Way's mass, close encounters with other stars, and internal dynamics all contribute to pulling clusters apart. Stars detach one by one until the cluster gradually fades into the general star field of the galaxy. Even our Sun originated from a stellar cluster long ago. Its siblings are now dispersed, dimmed, or lost in the haze of distance. The galaxy harbors ancient, hypermetal-poor stars. Among the rarest and most treasured objects in the Milky Way are hypermetal-poor stars. These are stars whose atmospheres contain virtually no elements heavier than helium. Some of these contain less than 1/100,000th the amount of iron found in the Sun. These stars are believed to be among the very first to form after the universe's initial supernovas, carrying only faint traces of enrichment from a cosmos still in its formative stages. They are incredibly ancient, exceptionally pure, and scattered throughout the halo like distant beacons from the dawn of time. Each one represents a form of relic, a luminous, gravitationally bound testament from a nearly forgotten epoch. Planetary systems form throughout the Milky Way. Planets are not an uncommon feature of the cosmos. They are a natural consequence of stellar formation. As a new star ignites, a rotating disk of residual gas and dust surrounds it. Within this disk, particles adhere to one another, accumulate mass, and develop into worlds. Across the Milky Way, planetary systems are widespread. Some are vast, featuring gas giants and frozen moons. Others are compact, with rocky planets closely orbiting dim stars. Some may bear resemblances to our own solar system, while others defy our expectations entirely. The galaxy is not merely populated by stars, it is teeming with systems, with solar families, each possessing its own unique equilibrium, orbital characteristics, and potential for development. Earth is situated near the co-rotation radius. Within the Milky Way, the spiral arms rotate at a different velocity than individual stars, behaving more like a propagating pattern than a solid structure. However, there exists a specific distance from the galactic center, known as the co-rotation radius, where the average orbital speed of stars aligns with the rotational speed of the spiral arms themselves. Our Sun's orbit is close to this boundary. This harmonious match in motion may shield us from frequent passages through spiral arms, regions characterized by higher stellar density, increased supernova activity, and gravitational disturbances. It is plausible that we inhabit a more stable galactic neighborhood, protected not by physical barriers, but by orbital resonance. The Sun bobs up and down through the galactic plane. As it orbits the Milky Way, the Sun does not follow a perfectly flat trajectory. Instead, it moves in a gentle wave, drifting above and below the galactic plane like a cork, bobbing in slow motion, rising and falling over periods of tens of millions of years. This vertical oscillation is caused by the gravitational influence of the galaxy's mass, alternately pulling and releasing the solar system as it progresses. Some researchers have even hypothesized that this motion might correlate with cyclical extinction events on Earth, although definitive evidence remains elusive. Nevertheless, it serves as a reminder. Even on its steady path around the galactic center, the Sun is not gliding smoothly, but is gently swaying through space. We do not comprehend the nature of dark matter, yet we are certain of its existence. Dark matter constitutes the majority of the Milky Way's mass, yet it has never been directly observed. It neither emits nor absorbs light. It passes through ordinary matter as if it were not present. However, its gravitational effects are undeniable. It is responsible for holding the galaxy together, explaining the unexpectedly high rotational velocities of stars, and shaping the formation of large-scale cosmic structures. Without it, the Milky Way would disintegrate. Astronomers detect its presence not by direct observation, but by monitoring its influence on other celestial objects. It is the galaxy's invisible framework, unseen, silent, and remaining one of science's most profound enigmas. There is more mass located outside the disk than within it. While the majority of the Milky Way's visible stars reside within the flat, luminous disk, the bulk of its mass is situated elsewhere. The galaxy is enveloped by an immense dark matter halo that extends far beyond the outermost stars. This luminous shell encircles our galaxy, exerting a far greater influence than its visible components. It harbors a sparse population of ancient suns and tightly bound star clusters, but its true mass remains concealed. When we envision the Milky Way, our minds conjure images of its spiraling arms and flattened starry expanse. Yet, this represents merely the luminous surface. The fundamental mass that defines our galaxy, its gravitational pull, its orbital dynamics, its very reach, is predominantly obscured, enfolding everything like a silent shroud. It is conceivable that the heart of the Milky Way once blazed as a quasar. Currently, our galaxy's core appears quiescent, yet evidence suggests a period of dramatically heightened activity in the past. The presence of immense gamma-ray structures, such as the Fermi bubbles, and traces of high-energy light reflected in surrounding nebulae indicate that the supermassive black hole at the galactic center may have once flared as a quasar, a brilliantly violent beacon fueled by inflowing matter. Quasars rank among the universe's most luminous phenomena, outshining entire galaxies. Had the Milky Way once blazed with such intensity, it would have presented a strikingly different spectacle, a spiral galaxy enfolding a blinding nexus of light. That era has long since passed, but its echoes persist. The architecture of galaxies undergoes transformation over eons. While galaxies may appear immutable, they are in perpetual flux. Spiral arms shift, galactic bars form and dissipate, and gas flows both inward and outward. Stars are born and expire, continuously altering the galactic population. Even the very shape of the Milky Way's disk, with its warps, ripples, and asymmetries, is undergoing gradual alteration. Encounters with smaller dwarf galaxies and the pervasive dark matter can bend or distort its structure. Over billions of years, the galaxy's silhouette has shifted like a drifting cloud. The Milky Way of today is neither the one that was, nor the one that will be. Its beauty resides not in permanence, but in its quiet metamorphosis. Gravitational waves propagate through our galaxy, originating from distant cosmic collisions. Across the vastness of the universe, colossal celestial bodies merge, black holes spiral into each other, neutron stars collide violently, and entire galaxies coalesce. These cataclysmic events generate gravitational waves, disturbances in the very fabric of space-time. Though incredibly faint, some of these waves traverse the Milky Way, causing minute distortions in space as they pass. Detecting them is an extraordinarily challenging endeavor, yet observatories like LIGO and Virgo have already registered several such ripples. New experiments are underway with the aim of detecting the ambient hum of gravitational waves that pervades the cosmos. Even now, as you rest, space-time itself is subtly shifting. The changes are imperceptible to our senses, yet they serve as undeniable proof that somewhere in the distant cosmos, the universe is undergoing transformation. Some stars follow elongated, inclined trajectories. Not all stars orbit the galactic center in perfect circles. A subset follows elongated elliptical paths, their orbits looping high above and far below the galactic disk, inclined at peculiar angles to the primary plane. These stars likely originate from diverse sources, perhaps remnants of dwarf galaxies absorbed by the Milky Way or survivors of ancient gravitational upheavals. Their orbital paths serve as invaluable clues, offering three-dimensional maps of the galaxy's turbulent past. By charting their movements, astronomers can reconstruct the invisible structure of the Milky Way's mass and its historical imprint. These stars drift like solitary messengers from disrupted systems, tilted and stretched, yet still bound to the galactic whole. Trillions of neutrinos pass through your body every second, originating directly from the stars, particles so ethereal we can barely detect them. These spectral particles are born from nuclear reactions within stars, from supernovae, and from cosmic rays colliding with atoms in space. The Milky Way is saturated with them, yet their minuscule mass and minimal reactivity allow them to pass through virtually all matter undetected. Specialized observatories, situated deep underground or beneath glacial ice, endeavor to capture even a handful of these elusive particles. Neutrinos carry vital information from regions inaccessible to direct observation, from stellar cores, from collapsing giants, and from the galaxy's hidden energy sources. They are the faint whispers of cosmic fire. The space between stars is not a void. It is a turbulent expanse. The interstellar medium, composed of tenuous clouds of gas and dust, is agitated by shock waves, magnetic fields, and the relentless motion of stars. Temperatures within this medium fluctuate dramatically. Streams of matter collide, mingle, and fragment. Clouds stretch, fold, and tumble. On grand scales, this creates a kind of turbulence, akin to a slow-motion ocean swirling through the galactic disk. Star formation, the propagation of cosmic rays, and even the broader processes of galactic evolution are all influenced by this restless medium. What appears from afar as tranquil starlight is, upon closer inspection, a dynamic, rippling fabric sculpted by unseen celestial winds and ancient energies. The galactic halo may harbor rogue planets. Planets are not invariably bound to stars. Some form through conventional processes and are subsequently ejected from their nascent systems. Others may never have been associated with a star at all. These are rogue planets, worlds adrift within the galaxy, cold, dark, and solitary. Although challenging to detect, studies indicate that billions of such planets may exist within the Milky Way, some even residing in the outer halo, where stars are exceedingly rare. Lacking light or warmth, they float unseen, warmed solely by their internal heat. They are the orphans of the galaxy, planetary wanderers traversing vast, lonely paths through the interstellar darkness. Magnetic fields dictate the movement of cosmic dust. Interstellar dust, composed of microscopic grains of carbon and silicon, is propelled not only by gravity, but also by the influence of the galaxy's magnetic field. These fields thread through the Milky Way like invisible currents, guiding the trajectory of charged particles and dictating the alignment of gas and dust. In certain regions, dust grains spin rapidly, emitting faint microwave radiation. In others, they align themselves with magnetic field lines, polarizing the starlight that passes through them. Understanding these phenomena enables astronomers to map the magnetic field structure and even to account for its influence in cosmic background radiation studies. Dust is not a passive constituent. It dances to a magnetic rhythm, revealing hidden patterns within the darkness. Some stars are enriched by the remnants of neutron star collisions. When two neutron stars spiral inward and collide, they trigger one of the most violent events in the cosmos, a kilonova. This brief, incandescent explosion forges immense quantities of heavy elements, including gold, platinum, and uranium. These newly created materials are expelled into space, intermingling with gas and eventually contributing to the formation of new stars. Certain stars within the Milky Way bear the chemical signatures of these rare cosmic events, enriched with elements that could only have originated from such cataclysmic collisions. They are not merely luminous celestial bodies, but living records of ancient cataclysms, blazing with the residue of stellar wreckage and cosmic alchemy. The Milky Way might possess a hidden bar within a bar. At the galaxy's core lies a stellar bar, an elongated bridge of light that traverses the central bulge. However, deep within this bar, astronomers have detected subtle indications of a second, smaller bar, tilted at a different angle and rotating independently. This inner structure is difficult to observe directly, obscured by dust and distance, but its gravitational influence is discernible in the motion of nearby stars and gas. Such bars are believed to facilitate the channeling of material toward the supermassive black hole, providing it with sustenance and shaping the dynamics of the galactic core. The center of the Milky Way is not a monolithic entity. It is a layered, dynamic labyrinth of light and motion. Intergalactic gas streams nourish the galaxy from the cosmic web. The Milky Way is not an isolated system. It draws fresh gas from the intergalactic medium in the form of tenuous streams flowing through the vast cosmic web. These inflows furnish the raw materials for new star formation, replenishing the galaxy's reserves over time. Some gas arrives as cold filaments, subtly entering the disk. Other streams descend in hotter, shock-heated forms, emitting light in the ultraviolet or X-ray spectrum. These unseen rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond. Even now, the Milky Way draws sustenance from distant reservoirs, nourished by threads of matter spun from the early cosmos. Hot gas forms towering chimneys that extend from the disk. When clusters of massive stars undergo supernova explosions, they create enormous cavities within the interstellar medium. These cavities can coalesce into superbubbles, vast pockets of hot gas that erupt upward through the galactic disk and vent into the halo. The result is a form of chimney, a conduit through which energy, gas, and magnetic fields escape from the galactic plane. These chimneys regulate the pressure of the interstellar medium, redistribute heavier elements, and contribute to shaping the halo's structure. In this manner, the galaxy exhales, not only within its disk, but through towering columns that channel its energy upward and outward into the darkness. The galaxy emits X-rays from aged stars and black holes. Although the Milky Way appears tranquil in visible light, it radiates intensely across other wavelengths. X-rays emanate from its core, from collapsed stars, and from the edges of black holes. White dwarfs and neutron stars in binary systems can siphon matter from their companions, heating it to millions of degrees. Hot gas in the halo also emits faint X-rays, revealing the galaxy's larger skeletal structure. We cannot perceive this high-energy radiation with our eyes. However, telescopes such as Chandra and XMM Newton depict a vastly different portrait of our galaxy. Not a serene spiral, but a realm of extreme temperatures, compact stellar remnants, and hidden radiation. Pulsars serve as cosmic chronometers throughout the Milky Way. When a massive star collapses to form a neutron star, it may begin to spin rapidly and with extraordinary precision, emitting beams of radiation that sweep across space. These are pulsars, and some rotate hundreds of times per second, pulsing with regular, measurable rhythms. Their consistency is such that astronomers employ them as cosmic timekeepers, utilizing their signals to measure distances, test theories of gravity, and even search for gravitational waves. Across the Milky Way, pulsars blink silently, remnants of stellar demise, yet also beacons of astonishing order. They mark time not in minutes or days, but across entire epochs, ticking with unwavering steadiness in the silence between the stars. Radio waves map the galaxy's hidden structure, A significant portion of the Milky Way is invisible to optical telescopes, concealed by dust, distance, or faintness. However, radio waves can penetrate these barriers, revealing structures that would otherwise remain unseen. They trace the distribution of cold hydrogen gas, delineate magnetic fields, and highlight emissions from pulsars, supernova remnants, and even distant quasars far beyond our galaxy. Utilizing arrays of radio telescopes, astronomers have charted the spiral arms, measured the warp of the galactic disk, and identified star-forming regions cloaked in darkness. Where visible light is obstructed, radio observations provide insight. The galaxy communicates in a language we cannot hear, but one that science has learned to translate into form and shadow. The sun likely originated in a stellar nursery. Stars rarely form in isolation. They typically emerge in groups. Stellar clusters coalesced from the same collapsing cloud of gas and dust. Our sun was almost certainly one such member. Eons ago, it shared its cosmic cradle with hundreds, perhaps thousands of sibling stars, all born from the same primordial nebula. Over time, gravitational forces, passing stars, and the galaxy's overall motion dispersed this cluster. Most of the sun's siblings have since drifted far apart, flung into disparate orbits, carrying with them fragmented memories of their shared origin. Some may still shine nearby, indistinguishable among the multitude of stars, lost kin within a sea of light. Astronomers are actively searching for the sun's dispersed siblings, stars that share its age, orbital characteristics, and chemical composition. Through extensive surveys like Gaia and sophisticated spectroscopic databases, researchers aim to identify these long-lost stellar relatives. A few candidates have already emerged, stars that may have shared our origin, having formed from the same enriched cloud of gas. If identified, they could unveil crucial details about the conditions under which the Sun and the early solar system came into being. Our place within the galaxy is not entirely solitary. Somewhere in the cosmic expanse, the Sun's ancient kin may still be shining. The galactic disk exhibits a subtle wobble as it rotates. The Milky Way's disk is not perfectly planar. It exhibits a gentle oscillation, rippling like a spinning plate that has been slightly nudged off balance. This warp is most apparent in the outer regions, where the disk bends upward on one side and downward on the other. It may be attributed to the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries within the galaxy. The wobble rotates slowly, akin to a vast wave propagating through the stellar population. From our vantage point on Earth, we do not perceive this motion. However, viewed from afar, the Milky Way is not a pristine spiral, but a dynamic, undulating sheet of stars, gently curving as it turns. Galactic tides can distort star clusters and stellar streams. Just as the moon's gravity generates tides on Earth, the immense mass of the Milky Way exerts tidal forces on all objects within its gravitational influence. Star clusters, satellite galaxies, and even globular clusters are subject to the galaxy's uneven gravitational pull. Over extended periods, these tides can stretch and deform them, drawing out elongated stellar streams or dislodging stars from their orbits. Numerous faint arcs of stars mapped across the sky are remnants of such gravitational interactions. Clusters in the process of disruption are being unraveled. Galaxies are slowly torn apart. The galaxy does not shatter these structures abruptly. Rather, it unravels them patiently, strand by strand, over millions of years. The total mass of the Milky Way remains uncertain. One might assume we would possess a precise measurement of our own galaxy's mass, but determining it is remarkably challenging. Stars and gas constitute only a small fraction of the total mass. The remainder resides within the vast, invisible halo of dark matter, which cannot be directly observed. Estimates vary considerably. Some calculations suggest a mass close to 1 trillion times that of the Sun, while others place it significantly higher. This uncertainty arises from the difficulty of measuring the orbital velocities of stars at great distances, a task complicated by limited data and the pervasive influence of invisible matter. The Milky Way is our home, yet its true weight remains a profound mystery. It may possess greater mass than Andromeda. For many years, astronomers presumed that the Andromeda galaxy, being slightly larger and brighter than the Milky Way, was also more massive. However, recent measurements suggest that the Milky Way's dark matter halo might be more extensive and denser than previously understood. If this is the case, our galaxy could indeed outweigh Andromeda, despite its more modest visible appearance. This finding has implications not only for comparative studies, but also for predictive models. When the two galaxies eventually merge, their relative masses will profoundly shape the dynamics of that colossal encounter. The Milky Way may appear serene, but beneath its placid spiral arms, it carries a greater heft than we once imagined. The Magellanic Clouds might be on their initial orbit. The Large and Small Magellanic Clouds, two prominent satellite galaxies visible from the southern hemisphere, have long been considered established companions orbiting the Milky Way. However, new evidence suggests they may be relatively recent arrivals, captured by our galaxy's gravity only recently in cosmic terms. Their velocity and trajectory through space hint that this could be their first close passage. If so, they are not ancient denizens, but distant wanderers just now succumbing to the Milky Way's gravitational embrace. Their arrival has perturbed the outer disk and subtly warped the galaxy's overall shape. It is as if the Milky Way is responding to the presence of a new gravitational guest, with the celestial quietude punctuated by the drama of first encounters. The Magellanic Stream is a ribbon of expelled gas. Trailing behind the Magellanic Clouds is an immense ribbon of hydrogen gas, a structure known as the Magellanic Stream. It stretches for hundreds of thousands of light years, forming intricate curves and arcs across the southern sky. This stream was gravitationally stripped away by tidal forces as the dwarf galaxies passed in close proximity to one another and to the Milky Way. Invisible in optical light, it reveals itself through radio wavelengths, a long trailing whisper of motion and cosmic attrition. This stream may eventually contribute to new star formation within the Milky Way, or settle into the halo, resembling a thread of memory stretching between galaxies. Some gas clouds orbit in polar directions. Not all constituents of the Milky Way adhere to the planar structure of the disk. Certain clouds of gas and even some stars follow highly inclined orbits, passing above and below the galaxy's principal plane. These polar orbits are likely the result of past mergers, when dwarf galaxies or stray gas clouds were captured at oblique angles. Over time, they continue to orbit along these tilted paths, much like comets orbiting a planet. These misaligned orbits serve as tangible records of cosmic disruption. They are visible reminders that the galaxy is not a self-contained entity, but an evolving structure shaped by the unpredictable flow of cosmic history. Giant shells of gas encircle remnants of past starbursts. In several regions of the Milky Way, astronomers have identified enormous spherical shells of gas, some spanning hundreds of light years. These shells are the remnants of powerful starburst events, periods characterized by the simultaneous formation of massive stellar clusters that lived brief, intense lives before exploding in rapid succession. The combined stellar winds and supernova explosions from these events carved out vast cavities in the interstellar medium, expelling gas outward in all directions. As the expansion progresses, it eventually slows, but the shells persist. These ghostly bubbles mark locations where the galaxy once blazed with intense stellar birth and death. They are the fossilized remnants of cosmic fireworks still echoing in the cold expanse. In dense stellar environments, stars occasionally collide. Space is vast, and stars are relatively small celestial bodies. However, in the most densely populated regions of the Milky Way, such as the cores of globular clusters, stars can approach each other closely enough to interact and even to collide. When this occurs, the consequences can be dramatic, resulting in a burst of light, the merging of two stellar bodies, or the formation of a rare blue straggler star, which appears younger than its stellar neighbors. While these collisions are infrequent, they are not impossible. Over billions of years, the most tightly packed stellar neighborhoods can undergo significant reorganization through gravitational interactions and sheer chance. In these crowded stellar cities, time appears to flow differently, and space is never truly empty. Binary stars can be torn apart by tidal forces. Many stars exist in binary systems, orbiting each other in a gravitational embrace. However, even this bond can be severed. If a binary system passes too close to the Milky Way's central black hole or traverses a dense star cluster, tidal forces can disrupt their orbits, potentially flinging one star away while the other is captured or its trajectory altered. In some instances, a companion star is ejected from the galaxy entirely, becoming a rogue star that speeds through intergalactic space. These stellar disengagements occur silently in obscure locations, a quiet severing of ancient partnerships by the inexorable hand of gravity. Some stars achieve escape velocity and leave the galaxy entirely. While most stars are gravitationally bound to the Milky Way, a select few occasionally attain escape velocity, exceeding 500 kilometers per second, and are hurled outward, never to return. These hypervelocity stars are rare but undeniably real. Some are believed to be ejected through interactions with the supermassive black hole at the galaxy's center. Others may be flung outward by three-body encounters or by supernova explosions within binary systems. Once free, they journey alone into intergalactic space, tiny beacons drifting far beyond the spiral's edge. They carry the galaxy's history outward, becoming solitary pilgrims in the vast darkness between galaxies. The Milky Way harbors stars originating from other galaxies. Not all stars within the Milky Way were born within our own galaxy. Some may have originated in other galaxies, captured during mergers or flung into our halo from distant regions of the local group. These intergalactic wanderers often follow unusual orbits far from the galactic disk, tracing paths through the outskirts or halo. They can be identified by their chemical composition or their peculiar motion, stars that do not quite conform to local patterns. Like cosmic immigrants, they bring with them narratives from different environments, distinct histories, and alien skies. The Milky Way is not a closed system. It is a living mosaic, slowly assembled through the passage of time and the interplay of motion, a galactic fountain of gas cycles between the disk and halo. Above and below the Milky Way's luminous disk, gas rises and falls in a quiet cycle known as the galactic fountain. Supernovas and outflows from stars energize and propel matter outwards towards the galactic halo, where it cools, coalesces, and gently descends over eons. This ongoing process agitates the interstellar medium, redistributes heavier elements, and aids in the regulation of stellar genesis. It represents a subtle exhalation and inhalation of cosmic material, a constant exchange between the dense galactic plane and the expansive halo. In this manner, the galaxy doesn't merely rotate. It circulates, breathing in and out, its structure maintained in perpetual motion across immense timescales. The galaxy's tiny dust particles are carriers of organic compounds. Within the nebulae of cosmic dust that drift between celestial bodies, researchers have identified intricate organic molecules, carbon-based compounds that serve as the foundational elements for life. These include polycyclic aromatic hydrocarbons, simple saccharides, alcohols, and more. While not alive themselves, they are chemically rich, originating from the atmospheres of expiring stars or within frigid clouds shaped by radiation. These minuscule grains, transported across vast distances by galactic currents, settle into the gas that coalesces to form stars and planets. Some may have even landed on early Earth. The galaxy's dust is more than just detritus. It is a payload of potential, silently traversing the void. Interstellar clouds may seed nascent solar systems with the very components of life. The crucibles where stars are born are also the birthplaces of worlds. As planetary systems coalesce from collapsing clouds of gas and dust, they absorb the chemical signatures of their parent nebulae. Should that cloud contain water, carbon compounds, and other prerequisites for biology, those ingredients may eventually reside within comets, asteroids, or planets. Certain regions within the Milky Way are particularly abundant in such prebiotic chemistry. While the prevalence of life remains unknown, the conditions conducive to its emergence appear to arise spontaneously. The embryonic forms of life may be dispersed widely, nestled within the galaxy's coldest cradles, awaiting an opportune moment to flourish. Some stars rotate at speeds hundreds of times greater than that of our Sun. Most stars exhibit rotation, but a select few spin at astonishing velocities, completing a full revolution in mere hours. These rapid rotators are typically young, massive, and inherently unstable, with their equatorial regions noticeably bulging due to centrifugal forces. A minority achieve such immense rotational speeds that they eject material, forming incandescent disks around themselves. Our Sun completes one rotation approximately every 25 to 35 days, depending on its latitude. However, these swift-spinning stars rotate hundreds of times faster, approaching the absolute physical limits of rotation. Their internal structures and evolutionary trajectories diverge significantly. Their lifespans may be fleeting, but while they endure, they whirl like alluring sirens in the darkness. The galactic plane is inclined relative to the ecliptic. From our perspective on Earth, the Milky Way arcs across the nocturnal sky as a graceful luminous band, yet it does not lie in the same plane as our solar system. The galactic plane, the flattened disk where the majority of the galaxy's stars are situated, is tilted at approximately 60 degrees with respect to the ecliptic, which is the orbital path traced by the Sun and planets. This inclination is the reason the Milky Way ascends at an angle and why its position shifts with the changing seasons. We are an integral part of the galaxy, but our own small system is positioned at a slight angle, akin to a small tilted vessel navigating a grander spinning cosmic sea. Some stellar remnants predate the galaxy's disk. Among the faint stars populating the halo, astronomers have discovered white dwarfs, the quiescent cores of once brilliant stars that are older than the Milky Way's thin disk itself. These ancient remnants originated when the galaxy was in its infancy, prior to the full stabilization of its primary structure. Their presence suggests an earlier era of star formation, a deeper history imprinted upon the outer halo. They have radiated for billions of years, gradually dimming, carrying with them the quiet remnants of a time when the Milky Way was still taking shape. The disk may be luminous, but the halo holds the memory of a more distant past. The most distant stars orbit far beyond the galaxy's central structure. The Milky Way's most remote stars trace their paths well beyond the familiar spiral arms, at distances of tens or even hundreds of thousands of light-years from the galactic center. These stars traverse the galactic halo along slow, expansive orbits, requiring billions of years to complete a single revolution. Many were likely assimilated from smaller galaxies during past mergers, now adrift in the outermost reaches like distant sentinels. They are faint, sparsely distributed, and widely separated, yet they contribute to defining the galaxy's dimensions, form, and gravitational influence. The Milky Way encompasses far more than what is readily visible. It extends deeply into the darkness, its form shaped by wanderers at its periphery. The Milky Way's configuration is asymmetrical in several respects. Although frequently depicted as a symmetrical spiral, the Milky Way exhibits subtle asymmetries. One side of the disk is noticeably thicker than the other. The spiral arms vary in their brightness and extent. Even the stellar halo is slightly off-center. These irregularities likely stem from gravitational interactions with clumps of dark matter or from past galactic mergers. The galaxy is not a perfect pinwheel. It is a dynamic entity characterized by pulls and twists, much like a spinning dancer whose skirt has been caught by the wind. Its beauty resides in this inherent irregularity, a graceful imbalance sculpted by the passage of time. Astronomers map the galaxy by utilizing variable stars. Certain stars fluctuate in brightness at regular intervals, expanding and contracting like slow, luminous heartbeats. These are known as variable stars, and specific types, such as Cepheids and RR Lyrae, exhibit a well-defined correlation between their luminosity and their pulsation period. By measuring the duration of a star's brightening and dimming cycle, astronomers can ascertain its intrinsic luminosity and, by comparing this to its apparent brightness, determine its distance. These stars serve as cosmic measuring instruments, assisting us in charting the Milky Way's dimensions, structure, and scale. They are lights that gauge the darkness, blinking beacons scattered throughout the spiral. The Gaia mission is profoundly transforming our comprehension of the Milky Way. Launched by the European Space Agency, the Gaia spacecraft is meticulously constructing the most precise map of the Milky Way ever conceived. By measuring the positions, movements, and brightness of over 2 billion stars, Gaia is revealing the galaxy's three-dimensional architecture and its evolution over time. It has uncovered stellar streams originating from disrupted galaxies, charted the subtle warp of the galactic disk, and traced the sun's orbit with exceptional fidelity. With each new data release, Gaia enhances our understanding, transforming a hazy expanse of stars into a sharp, dynamic map. It represents astronomy's most ambitious celestial chart, a silent revolution unfolding amongst the stars. The galactic plane marks a dense pathway of stars. On a clear night, away from the glare of urban lights, one might observe a hazy river of starlight stretching across the heavens. This is the galactic plane, the most substantial section of the Milky Way's disk. It is not merely a line, but encompasses a depth, a vast, flattened band where the majority of the galaxy's stars reside. Within this plane, stars are densely packed, dust layers are prevalent, and star formation occurs frequently. From our vantage point, we are looking along the grain of the galaxy, peering through its most richly populated corridors. This band is not only aesthetically pleasing, it is the bustling, humming heartland where most stars originate and eventually expire. The night sky appears brightest when directed towards the galactic center. The core of the Milky Way resides in the direction of the constellation Sagittarius, a dense, luminous concentration of stars, dust, and unseen mass. From Earth, we are unable to observe the very center in visible light. Clouds of dust obscure our view, but this region emits strongly in infrared and radio wavelengths. Even to the naked eye, the area appears more crowded and luminous, filled with the overlapping light of billions of stars. We orbit at a considerable distance from this core, in a tranquil suburban region of the galactic disk. However, when we direct our gaze inward, we are glimpsing the bustling metropolis at the galaxy's heart. We perceive the Milky Way's form from Earth. Because we inhabit its interior, we are unable to view the Milky Way from an external vantage point. Instead, we observe it from within, as a flat ribbon of stars extending across the sky, its curve defined only by the horizon. This internal perspective compresses the galaxy into a single arc, making it challenging to fully grasp its entire structure from our limited viewpoint. Centuries of observation, meticulous cataloging, and complex mathematical deductions were required to comprehend the spiral structure to which we belong. From Earth, we gaze through its disk as one might stand in a forest and look along the line of trees. We do not see the shape of which we are a part, only the immense expanse that surrounds us. The galaxy harbors far more than we can ever possibly perceive. Even with our most sensitive instruments, we capture only a fraction of the Milky Way's contents. Light is impeded by dust. Motion is concealed in silence. Dark matter vastly outnumbers luminous stars. Between every star lies emptiness, and within every void lies potential. It is what we surmise, what we infer, what we yearn to comprehend. It contains ancient light, future stars, drifting worlds, and questions that remain unanswered. And within that vastness, somehow we find ourselves, one planet among many, orbiting a quiet star, adrift within a narrative too grand for the eye to fully encompass. And now the stars begin to recede behind your thoughts. We have journeyed through 100 quiet truths, from the subtle warp of the galaxy's disk to the distant stars of the halo, from nascent suns to long-extinguished remnants, from dust and gas to light and shadow, and all that lies between. You have wandered through stellar nurseries, danced along spiral arms, and gazed towards the galactic heart, glowing behind veils of dust. You are an integral part of this galaxy, not merely a passenger on Earth, but an active participant in its lengthy and luminous unfolding. The iron within your blood was forged in the hearts of stars. The oxygen you inhale was sculpted by ancient cosmic explosions. The atoms composing your body trace their lineage back to the earliest epochs, born from the same matter that now fuels suns and whispers through clouds of interstellar dust. Tonight, as you rest, the galaxy continues its eternal motion. Stars are being born, light is traversing space, silent orbits persist, and you are floating within it, a small warmth in the darkness, residing in the spiral arm of a tranquil, radiant sea. If you happen to still be awake, you may proceed to watch the next chapter now. I hope you sleep soundly and dream gently. Good night. Thank you. Heat. Thank you. Heat. Heat. What are you doing?